As you can see from the periodic table, the majority of elements are metals, and these are generally located towards the bottom left portion of the table. One of the key characteristics of metals is that they form positive ions when they react. For instance, calcium forms a calcium 2+ ion. In contrast, nonmetals either do not form ions at all, like carbon, or they tend to form negative ions, such as the chloride 1- ion. To understand the reason behind this behavior, we need to revisit the concept of electron arrangements in atoms. Remember from our earlier discussions that all atoms aim to achieve a full outer shell of electrons to become stable. Elements positioned on the left side of the periodic table usually have only a few electrons in their outermost shell. For example, calcium, which is found in group 2, has just 2 electrons in its outer shell, making it relatively easy to lose those electrons and form a stable positive ion. On the other hand, chlorine has 7 electrons in its outermost shell, so for it to become a positive ion, it would need to lose all 7, which would require an immense amount of energy, something that simply doesn't happen in nature. Another important trait of metals is that they generally become more reactive as you move down a group in the table. This trend is linked to the number of electron shells the atoms possess. For instance, lead, represented as Pb on the table, has 6 electron shells, meaning its outermost electrons are located quite far from the positively charged nucleus. Since the nucleus is what holds the negatively charged electrons in place, the farther these electrons are, the weaker the attraction, making them easier to lose. This ease of electron loss explains why metals found lower down in a group tend to be more reactive. They lose their electrons more readily during chemical reactions, which is a defining aspect of metal reactivity. Now that we understand how metals and nonmetals differ in their electron configurations, let's take a look at how these differences affect their physical properties. First of all metals exhibit a type of bonding known as metallic bonding. This is a special kind of bond that is unique to metals and is responsible for many of their well-known physical characteristics. While we'll explore metallic bonding in detail in another video, for now just remember that these bonds are very strong. Thanks to this strength, metals are generally malleable, meaning they can be hammered or bent into different shapes without breaking, and they are excellent conductors of both heat and electricity, which is why they are widely used in applications like electrical wiring. Additionally, most metals have very high melting and boiling points. In fact, some metals can remain solid even at temperatures exceeding 2000 degrees. Other notable physical properties of metals include their shiny appearance and a quality called sonority, which means they produce a ringing sound when struck. In contrast, nonmetals usually appear dull, are brittle, meaning they break or shatter easily, such as the graphite in your pencil, and have generally low melting and boiling points. Many nonmetals exist as gases at room temperature, and they are poor conductors of electricity. They also tend to have lower densities compared to metals, which means they are lighter for a given volume. Finally, let's talk about the transition metals, which are located in the central block of the periodic table and are often colored green in educational diagrams. These can be considered typical metals because they possess all the general metallic properties we've discussed so far. However, transition metals also have some additional, unique characteristics. One such feature is that they can form ions with different charges. For example, chromium can exist as a 2+ ion, a 3+ ion, or even a 6+ ion. Moreover, these ions often exhibit distinct colors. The aqueous forms of chromium ions, for example, can appear blue, green, or orange depending on their charge. Perhaps the most practically significant property of transition metals is that they make excellent catalysts. A catalyst is a substance that increases the rate of a chemical reaction without being consumed or used up in the process. This is an important concept to remember. For instance, later in the course, you'll learn that iron is a crucial catalyst in the Haber process, which is used to produce ammonia, while nickel is used in the hydrogenation of alkenes, a process involved in the production of margarine. That wraps up today's lesson. We hope you enjoyed the video, and we look forward to seeing you again next time.